In this lesson, we're going to be introducing our new unit and actually an entire new section for the Calculus and Vectors course. So we're going to start by looking at an introduction to vectors. If you have some background in physics, this will start off seeming quite familiar to you, but as we move into different aspects of this, you'll find that the math treatment of vectors is going to diverge from the physics for quite a bit, and then later on, if you continue with math and physics, you'll find that they come back together again probably sometime during university. Some definitions we're going to want to make sure that we keep in mind as we discuss vectors, and you should have seen these before at some point in time in previous courses. The first one is the idea of a scalar. A scalar is just a number that you're used to dealing with, so it's a quantity that is specified by a number. And so some examples of scalars: area, temperature, speed, distance, length, those sorts of things. So we can represent those with numbers and the units that go along with them. A vector is something that is a quantity that represents both magnitude and direction. So it's not enough to represent it as a number. We also have to give some sense of direction. And that direction can be added, that information can be added a number of different ways. We can write it, we can use text, we can use arrows, diagrams, that sort of thing. And you can see a couple of very physics terms here. Force, definitely, and velocity, something we've talked about in the calculus and vectors course, but you really get a better treatment of velocity from a physics perspective. When we represent vectors, so when we're talking about a vector, we are worried about two things. We're worried about where the vector starts and where the vector ends, or where it goes to. And then, of course, we also have to worry about the length of the vector. So normally, when we start off talking about vectors, and a lot of the times in this course we're going to be talking about vectors between points. So A and B are simply points. So A and B on their own, they don't make a vector. They're just 2 points on a Cartesian plane, for example. And it is only when I join them, for example, AB with this little arrow above says the vector from starting at A and going to B. And the order that I put those, you can see it matters because these two arrows are different arrows. So this is the vector BA. But notice that the points A and B, they're in the same orientation with respect to each other. So to write these things differently, I just reverse the order, the starting and the ending positions. Another thing we'll do quite often when we're talking about vectors is we're going to talk about the size or the magnitude of the vector. And so that is represented using absolute value notation. And what that's essentially saying is, what is the size of this vector without worrying about the direction? And so once you take the absolute value of this, you now have a scalar value. This is just going to be a number. When we're comparing vectors, then we will say that they are equal or equivalent to each other under the following conditions. That's what this means. If and only if is a mathematical and a logical way of stating something. And it's basically saying I'm going to give you the criteria for this to be true. And you must satisfy all of these criteria exactly as they are stated. So in the case of vectors, for them to be equal to each other, first of all, they have to be parallel. They have to be parallel lines. They don't have to be coincident lines. They don't have to lie on top of each other. They have to be parallel. They have to have the same direction, and they have to have the same magnitude or length of the overall vector. So you can see here I've got two arbitrary points, A and B, and another 2 points, C and D, and I create two vectors from there. I create the vector AB and the vector CD. And because the vectors AB and CD share these three properties, that means they are equivalent vectors. Another thing, and again this is something we'll make use of course, because they're equivalent vectors, that means their magnitudes are also the same as each other. And so it's a bit redundant that I wrote this the way I did, but it's important to keep that in mind because sometimes you'll get this piece of information and that alone is not enough to work backwards to them being equivalent. And it says here, note that the starting point does not matter for equality. What that's saying is that if I take this vector and move it over here, it's in a new starting position, but it doesn't change the fact that these two vectors are equal to each other. You can also have opposite vectors. And again, they're a very specific set of circumstances to have opposite vectors. Opposite vectors are like equal vectors. The only difference is that the direction is exactly opposite. But you'll notice that they are still parallel. You'll notice they still have the same magnitude, but the direction is in the opposite direction. The way we represent that is we actually are saying that the vector AB is, and we use the minus sign to represent the idea of an opposite for a vector. So it has all the same properties as EF, except for you would have to multiply EF by a -1 in order to get them to be the same. And that is it. Very short lesson. Just a very brief introduction to vectors. The homework takes it a little bit further. There are some questions here that are still going to have you having to think about things a bit, but not very involved, and I think you can gather that from the length of this lesson overall.